Okay, so yesterday we discussed about the magnetic dipole, and our today's topic is Earth's magnetism. Earth's magnetism. In this under this topic, we will discuss about the magnetism of Earth. Okay, so first thing is, Earth also behaves like a bar magnet. Earth is having its own magnetic field, and the various properties of Earth's magnetic fields are, suppose this is geographical north here and this is geographical south. According to the geography of Earth, this point is called as the geographical north and this point is the geographical south. Similarly, we have, our Earth behaves simply like a bar magnet. It behaves as if a bar magnet is buried inside the Earth at the diameter, but that bar magnet is slightly, the axis of the bar magnet is not along the rotational axis of Earth. Okay, this is magnetic south and this is magnetic north. Okay, this point is magnetic south, this point is magnetic north. This is the axis of rotation. Okay, this is called as your geographical meridian. Geographical meridian. Okay, this is called as magnetic meridian. The line, the axis of the magnet, the axis or the line that joins magnetic south with magnetic north is magnetic meridian, and the line that joins geographical north with geographical south is geographical meridian. They are not actually the lines, actually they are the planes. Okay, if you cut the Earth, if you cut this Earth along the magnetic axis, along this magnet, then that plane which is cutting the Earth is magnetic meridian, and the plane that will cut passing through geographical poles will be called as the geographical meridian. Okay, the angle here in between the two is 20 degree approximately. Okay, at the center of the Earth, the angle between them is approximately 20 degrees, right? And this distance here, the distance of magnetic south from geographical north is approximately, this distance is 1600 kilometers. It is 1600 kilometers approximately. Okay, the distance between magnetic south and the geographical north is nearly 1600 kilometers. Okay, now the position of this magnetic south is 70.5 degree north. I'm telling you the coordinates of that position: 70.5 degree north and 96 degree west. This place is located in Canada. Okay, the position is inside the country Canada, and the magnetic north is 73 degrees south and 155 degree east. This is the position of magnetic north. Okay, then the plane which is perpendicular to the plane that passes through the center and perpendicular to the geographical meridian is called as geographic equator. Okay, geographic equator. Similarly, the plane which is passing through the center and perpendicular to the magnetic meridian is called as magnetic equator. Okay, and since the angle here in between the meridians is 20 degrees, similarly the angle between the equators is also 20 degrees. Okay, you can mathematically obtain also this, right? So this is about the magnetic, you can say the description of magnetic field of Earth, right? Now why this is magnetic south and this is magnetic north? The reason is because if you will suspend a magnet with the help of a thread, then that magnet always points towards a fixed particular direction. The north pole of the north pole of the magnet always point nearly towards the geographical north. Means from such a position you cannot understand that, you cannot conclude that the north, there is a difference between the geographical north and magnetic south. Means the magnetic poles are not located at the same position. You cannot conclude from here, from the center of the earth. So simply what I am saying here is, the north pole, when you hang a magnet with the help of a thread, right, it always points particularly in a fixed direction. The north pole of the magnet points towards the geographical north of earth, and the south pole points towards the geographical south of the earth. And this property makes it useful to makes it useful for the use of compass. Okay, a magnet is used in making of the compass. So this is the property which we call as the directive property. Always point along a particular fixed direction. Now, if the north pole is, as we know that the magnet is aligned in a particular fixed direction always, so it means that there should be some magnetic field which is attracting the poles. And if that the magnetic field should be in such a way that the south pole of that magnetic field, should be here near the geographical north. By doing this experiment, we can simply conclude that why magnet comes in a particular fixed position, because only reason is it must be attracted, the poles must be attracted by the poles of another magnetic field. Now, whose magnetic field that can be? It can be only the Earth's magnetic field. Now, what it simply says that north pole is pointing towards the geographical north. So it means that the south of that magnetic field must be near the geographical north. So that's why the pole here, which is near the geographical north, is termed as magnetic south. Okay, and similarly, the other end should be at the geographical south. Means the magnetic north should be near the geographical south. That's why the magnet always points along the north-south direction. The north pole of the magnet points towards the geographical north, because it is actually pointing towards the magnetic south. Okay, all right. So we can write few definitions also from here. What is geographical meridian? That I told you, that the plane which is passing through the geographical poles, geographical north and geographical south. Similarly, what is magnetic meridian? The plane passing through the magnetic poles. Okay, it is magnetic meridian. Then geographical equator, the plane which is perpendicular to the geographical meridian is the geographical equator, and the magnetic equator is the plane which is perpendicular to the magnetic meridian. Okay. All right. So there now few points can be discussed here. First is position of poles, and when we are talking about the poles, we mean with magnetic. The position of these magnetic poles continuously shift. They are shifting. They always continuously shift, right? They are shifting, right? The shift of poles is continuously taking place. Second point is that Earth's magnetism is due to the charged metallic fluid. Charged metallic fluid is the reason of Earth's magnetic field. Now here I would like to discuss with you the important theories that describe that what is the reason of Earth's magnetic field. However, none of them can be said, we cannot say that any one of them is completely true. Means we don't have any experimental reasons, but only we have predicted and we have the theoretical reasons also. So three different theories we have for the magnetism of Earth. First one is, we know that Earth is rotating on its axis, right? As a result, it means that everything which is on Earth is rotating, is revolving on a circular path. Suppose a body is there, then that body must be executing a circular path like this, right? Now it means that all the atoms, since Earth is everything on the earth is made up of, is constituted of the atoms. The smallest unit is atom. So it means that all the atoms, all the charged particles inside the atoms, they are revolving on a circular path, right? Now when a charged particle starts revolving on the circular path, it generates its dipole moment, and as a result it can create the magnetic field that we discussed in the previous topic. So similarly here, the first reason that people used to give for the as the reason of the magnetic field of earth is, first reason is that everything on the earth is revolving on a circular path due to the rotation of earth. As a result, they create a dipole moment, and hence earth gets its magnetic field. Now second reason, what the people say is that because of the rotation of earth, the atmosphere around it is also rotating, right? Now this atmosphere, when this high energy radiation comes from sun, it causes the ionization of these gases. Now due to the rotation of atmosphere, these ions are also rotating, are also revolving on the circular paths around the earth. Now due to their revolution, again, since the charged particles are revolving on a circular path, so it means that they will create a magnetic field. They will create they will have a dipole moment, and hence they will create a magnetic field. The third reason which scientists used to give is that earth at the center have a heavy metals at the center of the earth. The temperature and pressure is too high, and nothing can remain in the solid state there. So what we have at the center of the earth, at the core of the earth, is heavy metals like iron, nickel, cobalt. These heavy metals in the molten form, okay, in the liquid form. And since the earth is rotating on its axis, as a result, this high temperature fluid is molten. That molten state fluid is also rotating with the earth. And now these, since they have at this high energy level, at this high energy, when they are revolving on the circular path, they have the charged particles in them. So because of the revolution of those charged particles, earth gets its dipole moment. Now the three theories are different, but you can understand that one thing is common, that for all the theories, the reason is the rotation of earth. So one thing we can say is that the magnetism, the property of magnetism that is acquired by earth is because of its rotation on its axis. So the reason of earth's magnetic field is its rotation. Okay, so this was the reason of earth's magnetic field, right? Now one thing we can discuss on the topic, yes, that the poles are continuously shifting. We can have a small discussion on that topic also. This is earth, right? Now here we will discuss a small term called as solar storms. There is a particular term called as solar storms. Now what is solar storm? That sun is having actually the surface of the sun is very hot. It's too much hot. So what happens? Irregularly, a storm of charged ions, of charged particles with very high energy used to eject out from the surface of the earth, right? You can say a collection of charged particles with very tremendous amount of energy generally gets ejected out from the surface of the sun, right? Now this collection of charged particles is called as a solar storm, right? Solar storm. Now these solar storms they irregularly come out from the surface of the sun. Now what happens is, now since these are charged particles, so if they will hit the earth directly, if they will hit a planet, suppose we can take an example of earth, if suppose they hit the earth directly, then what will happen is they have a high amount of energy in the form of heat. They will evaporate the whole water of the earth, right? And they can destroy everything, right? Since they are magnetic also, since they are charged particles, so they will destroy everything that works on the magnetic field, like our computers, our satellites, okay? And as you know that nowadays most of the things, like suppose railways and most of the banks, most of the things they are working is relying on the use of computers, okay? some softwares are there. Now as you can see that we are getting our tickets reserved with the help of a online ticket, that reservation system is there. So it is also working on some kind of computerized program. So these computers means now the computers have become an important part of our life. Now when these charged particles, they will hit the earth, they will destroy all kind of magnetism. And since our computers also work, their memory, what is their memory? Like we say that they have two different types of memories, RAM and ROM. So they have nothing but only the magnets in there. And these magnets can be used to store the information. So there they are storing the information. Now if these charged particles will hit, they will destroy the magnetic properties. So the computers will lose their magnetic, their property of RAM and ROM, and therefore that operating system will stop working and everything will stop. So it simply means that we cannot afford these solar storms to hit directly to our planet. Now who saves us from this solar storms? It is actually the magnetic field of Earth. Now how the magnetic field of Earth is there? Suppose this is magnetic axis. Our Earth has created a shield of magnetic field around it. Now here we have the magnetic north, so the direction will be like this. Okay, Earth is creating a magnetic field around it, which is acting as a shield. Why? Because when these charged particles come here, since they are charged, so what happens? These charged particles, they move towards they are attracted towards the Earth, the poles of the Earth, the magnetic poles of the Earth, because the magnetic field will be strongest at the poles. So these charged ions, these charged particles, they will be attracted towards the poles of the Earth. Now when they will move towards the pole, most of them, because of their high inertia, will move straight, will go on straight. Only a few will come towards the pole of that magnetic poles of the Earth. Similarly here, a large number will pass through and only few will come towards the poles. Now what will happen when these charged particles, they will cross, however they are fewer in number now, when they will cross through the atmosphere of Earth, they produce light of different colors. Okay, and that lights of different colors, they are called as, in the northern hemisphere, they are called as northern lights, and southern lights. Okay, this is a commonly visible phenomena on the magnetic poles. The people, those who live there in Canada or like in Greenland, they generally watch these phenomena. Okay, you can go on YouTube and you can search, you can find out that just name like this, northern lights and southern lights, and you will get some few images that how these lights happens on the places near the poles, right? These northern lights, they are also called as aurora borealis, right? And these southern lights are also called as aurora australis, right? There are different names for these lights. Now what is happening actually, now I will come back to my point, that what is happening actually is these poles are continuously, they are in a state of shift, right? They always used to move a little bit, means they are shifting. So what will happen someday, a day will come when this magnetic north, which is here, and the magnetic south, however that time will be very large, but some day will come when this magnetic north will reach here and magnetic south will come here. During that course, there will be some time when this magnetic north, magnetic south will be here and magnetic north will be here, like this. At that time, suppose a solar storm comes, then what will happen? It will hit directly to the surface of the Earth, because now the poles are here, right? That solar storm will directly hit almost all the charged particles. They will hit directly, hit directly to the surface of the Earth. Okay, and what will happen? They will evaporate that all water, and that all things will happen that I discussed earlier. This is something which happened with the planet Mars. The scientists used to assume that earlier at some point of time the Mars was also having some water and they were having atmosphere also. Okay, However, that atmosphere was very thin, but they were having the water on the surface of the that the planet was having water on its surface. Now what happened, what scientists used to think that during their shift of magnetic poles, a solar storm must have collided, must have hit the surface of Mars, and due to that that hitting of that solar storm on the surface of the Mars, it has evaporated the whole water of the Mars. So scientists used to think that. So it means that I was just connecting it with the fact that the poles are continuously shifting on the surface of Earth. It happens with all the planets, right? Almost all the planets, not almost. I think all the planets are revolving, are rotating on their axis, and so all of them are having their magnetic fields, right? So, but that shifting of magnetic field goes on taking place, right? Okay, so this was mostly the theoretical part. Now we come on to the first important topic from this section, and that is elements of Earth's magnetic field. Elements of Earth's magnetic field. Elements of Earth's magnetic fields means that what are the different points that decide that how much will be the strength of Earth's magnetic field at a place. Means it will change from point to point or place to place. Then what are the various quantities, by measuring which particular quantities, you can tell that what is the nature of magnetic field at a particular place on the surface of Earth. So these are three elements. The three elements, by measuring them, you can tell the nature of magnetic field of Earth at a place. And the three elements are, first is your angle of declination. Which we will denote by theta. Second is angle of dip, that we will denote by delta. And third is horizontal component of Earth's magnetic field. Horizontal component of Earth's magnetic field, that is BH. Okay, Earth's magnetic field will have two components, vertical and horizontal. So horizontal component we will measure, and with the help of these three quantities we can identify the nature of magnetic field of Earth at any particular point on the surface of Earth. Okay, now we will discuss them one by one. Okay, first thing is, what is angle of declination? It is the angle between magnetic meridian and geographic meridian. Okay, angle between the magnetic meridian and geographical meridian at a particular place is the angle of declination, right? So how you will find out the angle of declination? We will suspend a magnet with the help of a thread at a particular point. Now we will have to identify the exact north-south direction. Suppose this direction is north-south direction, and this magnet, when I suspend it freely, it comes, suppose, in this position, like this. So this was, my hand was representing the north-south direction, exactly. It was representing the geographical north-south, means the geographic meridian. It is placed along the geographic meridian. The magnet will always align itself along the magnetic meridian. So when it comes this way, so whatever is the angle between them, is called as the angle of declination. So this way you can find out the angle of declination at a particular point. Okay. Next is the angle of dip. Now, okay. Now second is angle of dip. Now what is angle of dip? When you suspend a bar magnet, okay, then it always come into rest in this way. It will align, it will move on the, you can say this horizontal plane. It will move on the horizontal plane. This is north-south direction. It will move on the horizontal plane, as well as it will have a movement on the vertical plane also. It will dip also like this. Okay. So if this is north-south direction, and this is your north-south direction and the horizontal part, it will move like this, as well as it will have a dip vertical also, a change in angle vertically. So now what is the angle it has formed with the vertical, that horizontal, how much angle it has subtended vertically, that is your angle of dip. So what is happening actually, I can give you an example with the help of these pens. Alright, yes. Suppose the north-south direction, okay, this is your bar magnet. Now what will happen, it will come into rest like this. Okay, this is angle of declination, as well as it will move on the vertical plane also. So now this was your vertical, horizontal axis. So how much angle it has completed vertically, this angle, the angle between red pen and the blue pen. This is your angle of dip. Angle between this blue pen and the black pen, that is angle of declination. Okay, so angle of declination and angle of dip, we can measure them with the help of a suspended bar magnet at a particular place, right? Now the third one is your horizontal component of Earth's magnetic field. Now for that I will have to draw a figure now. Alright, suppose this is our geographic meridian and this is magnetic meridian. Okay, then this angle is your angle of declination, right? The angle is angle of declination. Now your magnet comes into state of rest like this. Suppose this is your suspended bar magnet. It comes into state of rest like this. So this angle this is the bar magnet, suppose. Then this angle, the angle drawn by the axis of the bar magnet with the horizontal, this horizontal direction is your delta. This is your angle of dip, right? This is your horizontal BH and this is BV. This is horizontal component of Earth's magnetic field. This is vertical component of Earth's magnetic field, and this is your B, right? The direction of in which direction the magnet will align. It will align along the direction of Earth's magnetic field. So this is the direction of Earth's magnetic field. Then this is horizontal component, this is vertical component. Therefore, how much is your BH? This is your horizontal component, so you can write B cos delta. How much is BV? Equals to B sin delta. So how much is BH upon BV? Equals to tan delta, right? So this is your BH upon BV equals to tan delta. Oh, sorry. Not BH upon BV, it should be BV upon BH. Because then only you will get sin delta upon cos delta. So it should be BV upon BH. Okay. So these are various formulas with the help of which you can calculate the value of B, as well as you can find out that in which direction the the magnetic field of Earth is aligned in which direction. Okay, right. Now we will discuss few properties, and these properties are important properties. Okay. First is, suppose this is Earth. Okay. Now this is your geographic meridian, this is magnetic meridian. Now if suppose on the when we will particularly talk about the angle of declination first, and then about the angle of dip. Now how the change of angle of declination takes place as a person moves on the surface of the Earth, that we are going to discuss. Suppose the person is at the equator, at the equator, someplace at the this geographic equator, right? Now when you will place a bar magnet, then in which direction the bar magnet will point? It will point like this. We are only talking about the angle of declination. So what will be the angle here? It will be 22 degree, right? Now when the person reaches here, okay, what will happen? Suppose this is the north pole and this is south pole of the magnet. This is magnetic south and this is magnetic north. Now the person moves here at this place, here. Now what will be the direction of magnetic, what will be the, how the magnet will align? What will happen? This north pole will be attracted by the magnetic south, and this south will be attracted by the magnetic north. Now when the person reaches here, when the magnet will be aligned at this place, so it will be aligned in such a way that, like this. This north will be attracted with the magnetic south. However, this south will also be attracted by the magnetic north, but the distance of this pole from the magnetic north is larger as compared to this distance. So the effect of magnetic south on the north of the magnet will be more. So it will be attracted in this direction. So what is happening now? Your angle is increased, right? When the person reaches at the pole, suppose, so this will be the direction, like this. This north will be attracted by the magnetic south and the angle will become almost 90, right? Similarly, if the person comes here, then now the south pole will be attracted. So now the direction will be like this. So your angle here is increased, and if the person comes to the pole itself, the geographical pole, then the magnet will align like this. This is south and this is north. So the angle will be approximately 90. So what happens as a person moves from equator to pole, right? That angle of declination changes from 0 degree to 30 degree. Not 0 degree, we should say yes, from 0 degree to 30 degree. Why we are taking here 0 degree? Exactly the reason is because I have simply shown this figure on a, it is not correct on the scale basis, because the size of the Earth is very large and this magnet will be definitely very much small. So when the size will be very small, so it will be very difficult to identify that in which direction the magnet is aligned. So what you will feel here is that magnet is aligned along the magnetic meridian only, right? So that means that at equator the value of theta is 0, and when a person moves towards the pole, the angle of declination increases to 90 degrees. So angle of declination changes from 0 to 90 degree as the person moves from equator to the pole. Now what happens to dip? What will happen to dip? Now again you can simply understand that if the person is standing on the equator, then the magnet with the is having a magnet, having a suspended magnet in his hands, and the person is standing on the equator. Now the distance of both the poles of the magnet from both the magnetic poles of the Earth is equal. So what will happen? Both the poles are equally attracted, so there will be no vertical tiltation, there will be no vertical angle will be subtended by the magnet, and it will be perfectly horizontal. So what is the angle with the how much angle it has subtended vertically? it will be 0 at the equator. Okay. Now the person moves to the pole and exactly reaches at the pole. Now when the person is standing at the pole, suppose I'm standing at the pole, then where is that magnetic pole? It is just under my feet, right? Suppose the person is here. So where is that magnetic south? It is nearly under my feet. So what will happen? This north of my magnet will be attracted by the magnetic south, which is under my feet. So this will be attracted like this. So that magnet will become vertical. So how much angle it has subtended with the horizontal direction, or how much angle it has vertically subtended? It is 90 degree. I mentioned here this as 30 degree. I'm sorry, this should be 90 degree. So you can see that in both the cases, suppose somebody moves from equator to the pole, both angle of declination and angle of dip, they both will increase from 0 to 90. Okay, at the equator both of them will be 0, and at the poles both of them will be 90 degree each. Okay. So this was about the elements of Earth's magnetic field. Now a small topic that which is magnetic maps. Okay. Now suppose you have suppose this is Earth. Now I took all the places which have equal value of angle of declination, right? Suppose I join all those places on the Earth with equal values of angle of declination, then I will get some lines on the surface of the Earth. Those lines, also called as the maps, are called as isogonic lines. Isogonic lines. Right? How you get? By joining the places of equal angle of declination. Right? If you join the places with equal angle of dip, then those lines will be called as isoclinic lines. Right? You can on the internet, or you suppose on on the YouTube, you can check these maps, the magnetic maps. You just simply you can write isogonic lines and you will get an image, and you can see that what type of maps are they in terms of images. Then isoclinic lines, when we join the places with equal angle of dip on the Earth, we get isoclinic lines. And isodynamic lines are there. Third one, isodynamic. If I join the places with equal BH, horizontal component of Earth's magnetic field, the maps that I will get will be the isodynamic lines. Okay, so these are different magnetic maps: isogonic with equal angle of declination, isoclinic with equal angle of dip, and isodynamic with equal value of horizontal component of Earth's magnetic field. Okay, now a method to measure the horizontal component of Earth's magnetic field. As I told you that angle of declination and angle of dip can be measured with the help of a bar magnet, with the help of a suspended bar magnet. Now how you will find out the value of BH? Right? For that we need to consider a concept, neutral point. Right? That I will tell you now. Suppose we have a magnet. I place a magnet with north, south, north towards the magnetic north, right? With the suppose geographical north, we will take first. Let us suppose that here we have the geographical north. It means that we have magnetic south here, and at this end we have suppose geographical south. It means magnetic north we have on this end. Now the magnet is placed in such a way that north pole of the magnet is placed towards the geographical north and south towards the geographical south. Now what is the direction of Earth's magnetic field? We know that it is from geographical south because there we have the magnetic north. So the direction of Earth's magnetic field is this one. Okay, like this. It is like this. Okay. Now what is the direction of magnetic field of this bar magnet? It is from north pole towards the south pole, like this. It is having this direction. So simply you can understand here that what is the direction of this magnetic field here. It is at the poles, means near the pole or on the axial line. What you can see that the direction of magnetic field of the bar magnet is similar to the direction of Earth's magnetic field. What is the direction here? It is like this. So you can see that the direction is upward. Here the direction of Earth's magnetic field is also upward. So they are adding each other. They are adding to each other, or you can say that they are supporting each other. Right? Whereas on the equatorial line, you can see that the direction of the magnetic field of the bar magnet is downward, whereas the direction of Earth's magnetic field is upward. Now the Earth's magnetic field, the horizontal component of Earth's magnetic field, right? This will be nearly constant at a place because the size of Earth is very large. So suppose in this region, which is equal to the size of the board, we can consider that BH will be constant. Okay. Now what about the magnetic field of this bar magnet? As you move away from the bar magnet, the strength of magnetic field will go on decreasing. Suppose BH is having a value of 5 here. Suppose in this place, right? The magnetic field of bar magnet here will be suppose 10, then it will decrease to 8, then it will decrease to 7, then 6, and there will be some point where you will get exactly 5 on the equatorial line. Now at that point, suppose this point, there we have 5. Now what is the magnetic field of this bar magnet? It is equal to suppose 5 units downward. Okay. What is the Earth's magnetic field? It is 5 units upward. So at this point, how much is the net magnetic field? At this point, what will be the net magnetic field? 0. There will be no magnetic field here. Similarly, you will get one more point at this end, right? You will get 2 points where there will be no magnetic field. It means that when you will place a compass here, the compass will not align in a particular direction. The needle of the compass will go on rotating. Okay, will start rotating irregularly. So these 2 points, they are called as the neutral points, right? These are neutral points. Now, what is happening here? The magnetic field of bar magnet is equal to BH, the horizontal component of Earth's magnetic field. Now, what is the expression to find out the magnetic field of a bar magnet on the equatorial line? The formula was mu naught upon 4 pi and m upon d square plus l square raised to the power 3 by 2 equal to dh. What is d? D is this distance, right? And what is L? L is half of the length of the magnet, the semi-magnetic length of the magnet, bar magnet. Bar magnet is like a dipole, magnetic dipole, so semi-length of that, half of the length of that. Or you can simply say that this length of the bar magnet, which length? The length between the poles is 2L. So this is your 2L. So using this formula, you can easily measure with the help of scale the half length of the bar magnet. Then you can measure with the help of scale, you can measure that what is the distance of this point where the compass is not showing a particular direction, right? By finding that value and substituting the other values, right? You can find out that how much is BH. What is the value of that horizontal component of Earth's magnetic field, right? Now you can put up an assumption also here. L will be very small as compared to D. This length of the bar magnet will be practically, this length is very small as compared to the value of D, because this point you will get at a large distance. So you can write here that BH is equal to mu naught upon 4 pi. This D square plus L square will be approximately equal to D square only. So square and half will cancel. So you will have M upon D cube. BH is equal to 4 pi into M upon D cube. What is M? M is the dipole moment. Okay. By this formula you can calculate the horizontal component of Earth's magnetic field. Again, there is another method, one more method, that if suppose you do not place this bar magnet in this direction and you place it just oppositely. Suppose we placed like this. This is the bar magnet, and now the south pole is towards the geographical north and north pole is towards the geographical south. So now again the magnetic field will be like this, but now the direction will be upward. Okay, now you can see that on the equatorial line the magnetic fields are supporting each other, because Earth's magnetic field is upward and these magnetic lines of forces are also upward. However, here the direction will be downward and here the direction will be downward. So what is the direction of Earth magnetic field on the axial line? Here it is upward. And what is the direction of the magnetic field of the bar magnet? It is downward. So this time where you will get the neutral point? On the axial lines. Here you will get the neutral point. Let us suppose that from the center of the magnet this distance is D and this distance is 2L. So now what will be your expression? Expression will be this time B of the magnet is equal to BH. Now what expression you will take? The magnetic field on the axial line. You will take that expression, and that expression is your mu naught upon 4 pi 2md upon your d square minus L square whole square is equal to BH. Mu naught upon 4 pi 2md upon d square minus L square whole square equals to BH. Now taking again, your L is very much small than D, so you can see, you can write that d square minus L square is approximately equal to d square, right? So it will become d raised power 4. Now this d and d raised power 4 will cancel, so you will get mu naught upon 4 pi 2m upon d cube is equal to BH. With this formula you can find out the value of BH. So finally, how can you find out angle of declination and dip? With the help of a suspended bar magnet. Experimentally you can easily find out. For finding BH we need to use this method. Okay, so by calculating these three values you can tell that what is the property, what is the nature of Earth's magnetic field at a particular place. So this was all about your Earth's magnetism, and tomorrow we will, means day after tomorrow, we will start the third section, which is about the magnetic materials.